let us continue with the left exercise of the coordination compound. So the first 16th question says that draw figure to show the splitting of d orbitals in octahedral crystal field. So the splitting looks like this. Okay, so this is the splitting. Now let us try to look at each of the terms that is given here. So first of all, we have a d orbital. We have the set of d orbital dx square minus y square, dz square, dxy, dyz, and dxz. Now, as soon as the ligand approaches, the energy of these ligands, the energy of this, say, orbitals rise. Okay, you can see here that the energy is raised. Now, why it is raising? The reason is that metals have electrons. Okay, orbitals have electrons in them. Okay, and when metal ligands approaches, they approaches through their orbital part. Since there is repulsion between the orbitals of the ligand and the metal, due to this reason, the energy of the d orbitals increases and move to this part. Now further, as the ligand approach closer and closer, there is a splitting of this orbital. Okay, now the splitting is such that the energy of this 3 and this 2, okay, if you just sum of the energy of these 2 and sum the energy of these 3, then this will be equals to the initial energy. So this is the kind of splitting that the orbitals goes. Okay, as orbital undergoes. You can see that it is being raised by 3/5 part on the upside, okay, and 2/5 parts on the downside. Got it? Okay. Now, if you just add this 3/5 and 2/5, you will get it as 1. Now, if I talk about the down one, then there are 3 orbitals, dxy, dyz, and dxz. Whereas the dx square minus y square and dz square are on the upside. Now, why is it so? What is the reason behind it? Say, what may be the reason behind it? Okay, here you can see that the orbitals or the dx square minus y square and dz square, they are along the axis. Okay, so if I just try to draw the orbitals of this compound, say the d orbitals, so how it would look like? So dx square minus y square looks like this. Okay, so these are the 4 lobes. Here is the x-axis. Suppose this is y-axis instead, and this is x-axis. Now you can see that the orbitals, the lobes are aligned along the axis. The lobes are aligned along the axis. This is termed as dx square minus y square. Whereas the dz square looks like this. So these 2 lobes are compared to this 4 lobes, these 2 lobes are longer. And it looks like this. So here we have the dz square. This is the shape of dz square. We have one more. Okay, so this is the complete structure of dz square. Now you can see very clearly that these 2 orbitals are aligned along the axis. This is aligned along x-axis and this one is aligned along x-axis and y-axis. Whereas in the case of the other one, that is dxz, dyz, and dxz, those looks like this. So suppose I am trying it for xy, then it would look like this. This is x, this is y. All of the orbitals are between the axes. Okay, here, 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 and here. So this one will be termed as dxy. Similarly, if you draw between x and z, it will be xz. If you draw between y and z, it will be yz. Now you can see very clearly that each of these lobes are not aligned along the axis. So this is the one thing. Now in an octahedral complex, the difference is that the ligands, when they approach along the axis. Okay, they approach along the axis. Now when they are approaching along the axis and these orbitals are also present along the axis, so due to repulsion between the lobes, the energy of this orbital rises. Okay, and at the same time, to maintain the conservation of energy, this energy drops. Okay, the energy of this orbital drops because they are not along the axis. Now, coming to the symbols, this is EG and this is T2G. Okay, this is T2G and EG. So T2G means triply degenerate. Okay, triply degenerate means 3 orbitals are there which are having the same energy. Degenerate means same energy. So this is triply degenerate and this is doubly degenerate. Okay, so E means doubly degenerate, and this one is triply degenerate. So EG and T2G. Okay, so this is the meaning of this. Why this G is here? One more thing. Why is this G here? So the G term is mainly for the G-rate. Okay, G-rate means suppose you draw an octahedral complex. Okay, so this is an octahedral complex. Then it would look like this. Okay, there will be 6 lobes. So I think it would be in this fashion. Okay, so this will be here. This will be here. One will be in this fashion. One will be here. And this is octahedral. Now if you look at the structure, so just draw the axis. If you move up and if you move down, okay, so you will find the same type, okay, same type of orbital. Similarly, if you move in this direction and you move in the alternate direction, you will find the same type of structure. Now, in this kind of structure, what it is said that they are G-rayed. Okay, G-rayed means both in the positive and negative direction, the thing is same. Okay, you can either say that it is symmetrical. Whereas in case of tetrahedral, you will not find this T2G. You will find only E and T2 because they are not G-rayed. Okay, so this is the overall splitting of the d orbital, and you must be curious about this T2G and EG. So I have explained each of these terms. Right? Now, let us look at the explanation. The splitting of d orbitals in octahedral complex placed in such a way that the dx square minus dz square experience a rise in the energy, whereas the EG level, that the dxy, dyz and dxz experience a fall in energy and form the T2G. Next is what is a spectrochemical series? Explain the difference between a weak ligand and a strong ligand. So what is spectrochemical series? So basically, if you see a ligand, you will see that there is a repulsion between the molecules, right? There is a repulsion between the orbitals. Now, if the donation power is better, okay, so if some ligand is donating more appropriately, then it will result in a more repulsion because the electrons will be more directed towards the metal ion. Due to this, the energy gap increases. Okay, energy gap increases, and since the energy gap increases, so whenever you feel the electrons, they do not go on the upper energy level. Suppose in case of octahedral, we have dx square minus y square and dz square on the top side. Now, since the energy gap is very high, right? Energy gap is very high. Therefore, they find it difficult to go on the upside if the ligand that is approaching is strong enough, because it has splitted it on the large scale. Clear? So, on the basis of the donation that is being available for the different ligand, this spectrochemical series is made. Okay. Now, the weak field ligands. What is the weak field ligands and strong field ligands? So, I have told you just now. So, if the splitting is large enough, okay, so if you see the splitting of the orbitals, if it is large enough that the electrons cannot be filled on the upper level until the down level is filled, okay, then it is called as strong. And if the splitting is small, such that after filling it half, it can go on the upside, then it is weak field ligand. So we will see this, okay. So a spectrochemical series is the arrangement of common ligand in the increasing order of crystal field splitting. As I have told you, the one which splits more is a strong field ligand. The ligand present on the RHS on the series are strong, okay, whereas the LHS are weak. So this is the series. So this one is, if I talk about the strong one, then CO is a strong one, FAN is a strong one, NO2, SO3 2 minus ethylene diamine. Now these are the moderate ones up till NCS minus, and from this we have the weak ligand. Now this is not the case each and every time, okay. It will totally depend upon the metal ion that one is dealt with, okay. So for I'm talking in general that up till En we have a strong field. For this part we have a weak field and moderate field, and this is the weak field. I will put I have put a more general, I put a more accurate picture of this in the previous lecture. Okay. So this is the CFSC. Now, if I ask you one more thing, that which of these is forming a strong field, then you will see that the carbonyl and the this carbon related ligands are more stronger, in which the carbon is present. This is always not the case. You can see the C2O4 minus is present here, but this is often the case. Clear? Got my point? Now, for a strong field ligand, what is the thing that we have a pairing energy and we have delta O, that is the splitting. In case of suppose extraordinary, I'm just writing it delta. Now, if the pairing energy is more, if in pairing the electrons, the energy required is more and the delta energy is less, then what will happen? In that case, the ligand will be what? The ligand will be weak ligand. Will be weak ligand. And if the delta is less, suppose I'm taking this octahedral, delta is less and pairing energy, delta is more and pairing energy is less. Okay, then in that case it is termed as strong ligand. Now this delta O will depend upon, of course, mostly on the ligand, but also on the metal ion and on the charge of the metal ion. Okay. Next is, what is crystal field splitting energy? How does the magnitude of delta O decide the actual configuration of d orbital in a coordination entity? So what is crystal field splitting energy? So whenever you split orbital, there is a CFSC energy that is being calculated. You must have calculated filling the electrons for each of this multiplied by 3 by 5 and 2 by 5. So that is the crystal field stabilization energy. So due to splitting, the amount of stabilization that has been occurred in the coordination compound, or the energy by which the coordination compound is stabilized due to splitting, is called as crystal field splitting. Now, how does this magnitude of delta O decide the actual configuration of d orbital? So of course it decides, we have seen it just now, pairing and not pairing totally depends upon the actual configuration of delta O. Okay, so if it is had to be paired, then what should be the case for pairing? That P should be less than delta O. Okay, and for the opposite case, there will be no pairing. Okay, so you can clearly say that delta O will decide the actual configuration of d orbital in the coordination entity. So the splitting of the d-gender level due to presence of ligand is called the crystal field splitting, and the energy difference between the two levels, Eg and T2G, is called as the crystal field stabilization. Or you can also say the energy by which the coordination compound is stabilized is termed as crystal field stabilization or crystal field splitting energy. It is denoted by delta. Since O should not be here, so in case of octahedral it is delta O, in case of tetrahedral it is delta T. Now, after the orbital has splitted, the filling of electrons take place after one electron has been filled. The 3T2G orbital, the filling of the fourth electron takes place in two ways. So it can either enter the EG orbital, as I have told, or the pairing of the electron can take place. So it will totally depend upon the delta O and P. Now, if the delta O of the ligand is less than the pairing, okay, delta of the pairing is less than the pairing, the electrons will enter the EG orbital, that is the high orbital. Now, if delta O is more than P, then the pairing will take place. Okay, clear? This point is clear. Now next, we have this thing. This question says that CrNH3 whole 6 3 plus is paramagnetic, while NiCN4 2 minus is dimagnetic. Explain why. So for this, you have to know the electronic configuration. First, you will draw the pairing, fill the orbital, do the pairing whether the ligand is strong or weak on the basis of that, and then you will decide that is paramagnetic or dimagnetic. So if I talk about this, then Cr is in the +3 oxidation state and NH3 is a weak ligand. As I have told you, it is moderate, but since moderate can be on the either side, so in this we have taken it as weak ligand. So their pairing does not take place, and since pairing does not take place, this configuration looks like this. Okay, right? After that, what will happen? You can see clearly that there are free electrons and unpaired electrons. So it is paramagnetic in nature. About NiCN4 minus. So Cn minus is a strong ligand. We have seen this. It is already a strong ligand. You don't have to think about the moderate or that part. So it will not show pairing. Instead, it will first fill off all of this. Sorry, it will show pairing. And since pairing will be done and no unpaired electron will be left. Okay, you can see here. So due to this reason, we will have paramagnetic and diamagnetic for two different structures. Next question. A solution of NiH2O whole 6 2 plus is green, but a solution of NiCN4 2 minus is colorless. What is the reason behind it? So the reason lies in the electronic configuration. So the d electron from a lower energy level can be excited to a higher energy level, that is the possibility of dd transition is present. Hence NiH2O whole 6 2 plus is colored. Okay. Whereas in case of the electrons are all paired, as Cn is a strong field ligand and the dd transition is not possible, and NiCN4 2 minus is colorless. So this is the reason behind it. Next is FeCN6 4 minus and FeH2O whole 6 2 plus are of different colors in dilute solution. So again the same reason, Cn minus is a strong ligand and H2O is a weak ligand. So this will result in two type of configuration, hence the color is different. So the color of particular coordination component depends upon the magnitude of delta, and this CFSC in turn depends upon the nature of ligand, as I have told you. And since Cn is a strong ligand and H2O is a weak ligand, okay. Therefore, we will see difference in color due to the difference in CFSC, because the color is coming because of dd transition, and dd transition is totally dependent upon the energy gap, right? So if the energy gap is changing, the dd transition will change, or the extent of dd transition will change, and hence we will see that there is a, you can say, there is a change in color of both the complexes. Next, we have to give the oxidation state of d orbital, occupation, and the coordination number of the central metal in the following complexes. So oxidation state, d orbital occupation, and number of the central metal ion in the following complex. So in this case, you will see what is the oxidation state, K3CO C2O4. So let us write this complex here, K3CO C2O4. So this is whole thrice. So K3, each potassium has the oxidation state of +1. So 3 into +1. Next is cobalt. So we are assuming it as X. C2O4, each will have a charge of 2 negative, 3 are present. So 3 into 2 negative. And the complex is overall having a charge of 0. So X minus 6 plus 3, that is +3 oxidation state. So oxidation state is +3. What about the d orbital occupation? So C2O4 is a weak ligand, if you remember, and cobalt has the oxidation state of how much? 3 to the 6. So 6 is 6 minus 3, 3. But cobalt is an exception. Okay, so cobalt is an exception. So this is an exception. Why? You will see that instead of weak ligand, this will show pairing. Okay, cobalt will show pairing. So if you talk about the electronic configuration, so we have potassium, calcium, scandium, titanium, vanadium, chromium, manganese, iron, cobalt. It has 9 electrons plus 3 oxidation state. So it will have 2 minus, so 9 electrons are there, na? 9 minus 3, that is 6 electrons, total of 6 electrons. So D6 will be present, right? D6 will be present. If I just draw it, and it will be paired. Why? Because CO2 is an exception. So 1, 2, 3, 4, 5, 6. So this will be the electronic configuration. Now if I talk about the, say, our hybridization, then it will be D2, and since C2 for 6 electrons are been donated, Therefore, we can write it as D2SP3. 1, 2, 3, 4, 5, 6. So this will be the case. Next we have cis, CR2, CR2, EN whole twice and CR. CR. So let us just see the first one. Okay. So the first one goes like this, +3 oxidation state, and this is having a pairing. So we are having pairing of each of these. Clear? What about cis one? So about this, so if you find the oxidation state, it comes out to be 3. So for ethylene diamine, it is say neutral, so 2 into 0. Cl2 each will have a negative charge, so 2 into -1, and overall there is a chlorine that is present outside. So the coordination entity has a charge of -1. Okay. So they have put it -1, and finally it will give you +3. Sorry, +1, so it will give you +3. Next, and since 3 electrons are present, so you don't have to worry about pairing and all. So 3 will be here. Next is CO4. Okay, COF4 and NH4 whole twice. Oxidation state. What will the oxidation state? NH4 whole twice means this is positive. Okay, so there are 2 of this, so each will have a +2. Right, +2, and this will be -4. So -4, -2, hence it will be +2. So how it is done? So let me draw it by my way. Okay, so I'm doing it in my way. So NH4 whole twice. So 2 NH4s are there, each will have a charge of +1. So 2 into +1. Done. Cobalt has a X, fluorine has a -1. So -1 into 4. This will give you 0. So 4 minus 2, 2. So they have done the same thing. They are putting this thing here. Okay. So +2. Now again, our fluorine is a weak ligand. So therefore it will not show pairing. So if you just try to fill this one, so we have 2 on the upside and 3 on the downside. Total of high electrons, how many electrons are there? 7. 1, 2, 3, 4, 5, 6, and 7. Therefore T2G3. Okay. EG4 and T2G3. So since it is a tetrahedral, not a octahedral, the splitting will be reversed. 2 here and 3 here. Now we can draw it. Here. One more thing to remember here is that the tetrahedral will always form a high spin complex. Means pairing will not take place first. First all of the d orbitals will fail, and then the pairing will take place. What is the reason behind it? If you remember the relation between the delta T and delta O, that you can clearly remember that delta T is less than delta O. Delta T is equals to 4/9 of delta O. Okay, so from this relation you know that delta T is very small. So since delta T is very small, so pairing will never take place. So first of all, the electrons will be filled in all the d orbitals, and after that the pairing will take place. Next we have this compound. Suppose manganese will have X, H2 is a neutral one, so it is 0. SO4 is having -2 charge. Overall is 0. So X is equals to +2 oxidation state. And this is a weak ligand, right? And manganese in +2. So potassium, calcium, scandium, titanium, vanadium, chromium, manganese. Manganese having 7 electrons. 7 minus 2, 5. So T2G and EG. T2G, since is octahedral, so 3 will be down, 2 will be up, 1, 2, 3, 4, 5. No pairing, okay? So this is T2G 3 and EG 2. Clear? Next is write down the IUPAC name for each of the following complexes and indicate the oxidation state. How we'll do it? And next we will write the electronic configuration and the coordination number also. So first of all we will write the name. So for the first one, Okay. The name will be potassium. So what is the first compound? So first of all, write this one, potassium. Then we'll write the name of the ligands. Okay. What are the ligands? Aqua and your oxalato. So since aqua comes first, so diaqua and dioxalato. Then chromium will have oxidation state of how much? See, C2O4 2 minus is minus 2. 2 into minus 2, that is 4. Potassium is plus 1. Chromium is supposed to be X. This is 0. This is 0. And overall charge is 0. So X will be 2 to the 4 minus 4 plus 1. That is plus 3 oxidation state. So chromium will be plus 3. Okay. So chromium 3. And then your crystal of water. So the name would be potassium diaqua dioxalato chromate 3 trihydrate. And this will be the electronic configuration. T2G3. So no pairing, you don't have to think about pairing because 3 electrons are only present. Next we have CONH3 whole 5 Cl2. How we will write it? First of all, the ligand name. Amine will come first, then the chloro. So pentaamine, chlorido, cobalt. What is the oxidation state? 1 Cl minus is outside, minus 1, and 2 are outside, again, minus 2. X is equals to 0, X is equals to plus 3. So 3 is the oxidation state of cobalt. Then we have chloride on the outside. Okay. What about the electronic configuration? So manganese, iron, cobalt. Manganese, iron, cobalt. 8 electrons are there, 3 are gone. Okay, so we will remember D5. Now again, I have told you that cobalt is the exception, so it will show no pairing. So it will show pairing. Instead, it is a weak. We are having weak ligand because it is cobalt 3 plus, so it will show pairing. So T2G5. You can see here. It is T2G5. Next question. CrCl3 Py3 pyridinium. Okay. So chloro will come first. So trichlorido, tripyridinium. Since pyridinium is a neutral one, so you don't have to add O. Okay, like in the case of chlorido. Then chromium. Okay, this is minus 3, so overall compound is positive, so 3 oxidation state. Pyridinium is neutral. What about this? So metal ions come first, so first we write cesium here in front of this, then tetrachlorido, after that we have iron. What will be the oxidation state? Cesium will be plus 1, chlorine will be plus minus 1, and 4 are present, so minus 4. X is equals to 0. 4 minus 1, 3. So plus 3 oxidation state. What about this? So this is plus 4. This will be X. 6 CNs are there, each with a negative sign. Is equals to 0. Okay, so X will equals to plus 2. So we'll write potassium and then hexacyanide, manganese, oxidation state is plus 2. What about the splitting? Again, see, chromium is in plus 3, but weak ligands are present. Potassium, calcium, scandium, titanium, vanadium, chromonium. Potassium, calcium, scandium, titanium, vanadium, chromonium. Okay, so 6 electrons are there in chromonium, 3 are been removed, so it will be T2G3. Okay. In case of iron, manganese, iron, cobalt, nickel, copper, zinc. So potassium, calcium, scandium, titanium, vanadium, chromium, manganese, iron. Iron is having 8 electrons. Okay. 8 electrons, 3 are removed, so it is D5. And since weak ligand is present, so no pairing will take place. So it will be T2G3 and Eg2. Last one, it is manganese. Strong ligand is present, so pairing will take place. So chromium, manganese, iron. Manganese is D7. 2 are removed, it is D5. And D5, it will be paired. So 4, 6, 5 will be present on the downside only. So T2G5. So this is the answer. Next we have, so this is the answer. 6, shape is octahedral. What about the shape of each of this? Say, so this will be tetrahedral, this will be octahedral, and this will be also octahedral. Further, we have to also calculate the magnetic moment. So since 3 electrons are unpaired present, so we will we'll take the formula n into n plus 2. 3 we will put and we'll get it as 15. Next we have, so you can just check this out. So T2G6, all electrons are present on the downside. So it was not T2G5, it is T2G6. Okay. As I have told you, it is plus 3 oxidation state. So it will be forming a weak field. Sorry, strong field. Magnetic moment is 0, all electrons are paired. What about this? It is T2G3 again. Condition number 6. The magnetic moment will be again root 3 into 3 plus 2. Next we have CsCl4 plus 3. It is weak field. And number of unpaired electrons are 5. That is maximum. So it will be 6. What about this? So it will be T2G5 again. As I have told you, it will be strong ligand. So all of the electrons will be on the downside. So unpaired electrons will be 2. Sorry, 3 and 2, 5, 1. Okay, 1 electron, an unpaired electron, hence 1.732. Explain the violet color of the complex of titanium H2O6. So this violet color, if you see of titanium, then you will find that titanium is having no unpaired electron. Okay, potassium, calcium, scandium, titanium. 4 electrons are there and all are removed. Okay, all are removed. So it will be in the plus 1 oxidation state. Only 1 electron will be removed, present. Weak field or strong field doesn't matter. So this is the thing. So instead of the presence of, say, weak field, this show the violet color. So this is mainly due to John-Taylor distortion. Okay, this is John-Taylor distortion. The stability of the coordination compound in a solution is the level of association. Stability of ion can also be explained in terms of formation is constant or stability constant, which is beta. And beta is given by this. Now the greater the value of beta, the stronger the metal ligand bond is. Okay, so charge on the metal ion, nature of the ligand. So all of these are responsible for our say complex. Right. Next question is, what is meant by Chillet effect? So Chillet effect is mainly shown by the compound which forms a cycle. Okay, which forms a cycle upon coordination. Like the example, and why is the Chillet effect so stable? Because the spontaneity decreases and delta is positive. Right. So if you take the case of the hexadentate ligand, okay, so that will show a Chillet effect. If you remember the example, 1,3-hexamethylene diamine. Okay, so that was the example of EDTA. Okay, ethylene diamine tetraacetate. It is a hexadentate ligand and it shows Chillet effect. They form a ring, and you can see that the log beta is more for the Chillet ligand. It is 18.1. Clear? Discuss briefly, given an example in each case, the role of the coordination compound. So this I am leaving it to you. Okay, so this you can do it by yourself. Okay. Next we have, How many ions are produced when the complex of CONH3 in the solution? So when you keep it in solution, how many ions are produced? 2 ions are produced, right? Sorry, 3 ions are produced, right? 3 ions are produced. Among the following ions, which of them has the highest magnetic moment? So for this, we will write the electronic configuration first of all. We will get that 3 unpaired electrons are present. We will use the formula and find it as 4. Okay, for second one, if you find, then you will get that the total number of electrons is unpaired electron is 4, and this will give you root under 24. Next is for zinc. You will find that there are no unpaired electron, so it will have the magnetic moment of 0. Next is among the following, the most stable complex is which one? So the one with the greatest SATHEE energy is the most stable. So what we will do, we'll find the SATHEE energy of each of this. Okay, and then we'll try to find out. But you will find that some of this will have the same SATHEE energy. Then it will totally depend upon the chelate effect. And since C2O4 can show a chelate effect, you can see formation of ring is taking place, and hence this will be the most stable one. Last question. What will be the correct order for the wavelength? Okay, so again it will depend upon CFSE. Now CFSE depend upon the nature of ligand, and we know that the NO2 is the strongest one, then the NH3 and then the H2O. So the energy will be in this order and the wavelength will be in the opposite order. Okay, you can see here. So this is a complete exercise. Okay, so with this we have completed the exercise of coordination compound. Next class we will move to NCERT exampler.